My computer freaked out earlier today, so hopefully it doesn't hear. Okay, so we're going to introduce something very interesting today. Something that you're going to think, oh, that seems kind of stupid to do that. But in the long run, I'm hoping by the time we're done today, you'll see, oh, maybe that's not as dumb as I thought it was. And then over the next couple of days as we discover some other things, and then when we get into the next unit, you're going to go, oh, wow, this is kind of cool that we can do this. So if you'll be patient over the next couple of days, we're going to just walk our way through some stuff and reason the way mathematicians did when they were coming up with ideas like this. Okay? Now, to his credit, Mason yesterday said, hey, what about these? And that's what we're going to talk about today. So Mason's going to maybe have a little bit less discovery than most of us do. So here's the objective for today. Here's our I can. I can understand and use, would you write the word radian? Radian measure for common angles. Now, we used the word common angle yesterday. We're using it again today with another vocabulary word. So the word is radian. Okay? So again, we kind of need to just carefully walk through, and I need you thinking about why this works, because in the end, the assignment is not very difficult. Okay? Our goal is this statement right here. Understand and use radian measure for common angles. So it says label all the common angles as for the first quadrant of this circle, and by convention where is 0. I'll give you 10 seconds. So right over here, what are you going to mark down? Okay, Wilson, I start at 0. What's the next one?
30.
30. What's the next one?
45.
45. What's the next one?
60.
60. And the last one?
90.
90 degrees right there. Okay? What is the formula for the distance around a circle? Don't say anything out loud. If somebody phrased it like that, it sounds kind of funny. We usually use a different word for it. Dane?
2 pi r.
2 pi r. What do we normally call it?
Circumference.
The circumference. So that's going to be 2 pi r. Okay, now, if you've been in my class before, you've heard this, and I think I've mentioned it even in this class, but if you were in my class last year, you definitely heard this. What is a conversion factor? It is a funny-looking... Conversion factors are really weird, but this is what they are. What are they? They're a funny-looking one. They're a funny-looking one. So we're going to use some conversion factors, and we're actually going to discover some conversion factors today. And the first thing we're going to do is something that you've probably done in a science class. We're just going to do a little bit of converting here. So I want to convert inches into feet, and I need to take advantage of something. And that's this, that everybody knows. 12 inches is exactly the same thing as 1 foot. So 12 does not look the same as 1. But 12 inches is the same thing as 1 foot. So if I'm going to convert 30 inches into feet, so I'm going to write 30 IN, I want to convert that into feet. Now you can probably in your head figure out what that is. Okay? But I want to take 30 inches and I want to change the units of measure from inches to feet. And I'm going to use that fact right there. Okay, so from science, does anybody remember what you do with this? Wilson?
Divided by 12.
Kind of. Yeah. Kind of. You're not wrong, but this is really what we want to do. What we want to do is we want to multiply by that by something. Now, you said divide by 12. Here's why we're dividing by 12. Because 1 foot is equal to 12 inches. And now I want you to notice that this is a conversion factor. Is this a 1? Yeah, technically it is. Does it look like a 1? No, if you brought an elementary school kid in here and said, hey, is 1 over 12, is that a 1? They would say no. And if there weren't units on here, the answer is no. But is 12 feet exactly the same thing? Sorry, 1 foot exactly the same thing as 12 inches?
Yes.
It is. So do we have the same thing on the top as we have on the bottom? Same thing over same thing is a 1. If you have the same thing on the top of a fraction as you have on the bottom of a fraction, it's a 1. So does everybody agree that that conversion factor is a funny-looking 1? And notice what happens. The inches go away. The only unit left is feet, And then on our calculator, we're going to throw in 30 divided by 12. And our calculator is going to say, and because this is kind of a story problem, we get the luxury of saying 2.5 feet. It did say feet, right? So we've got the right units on there. So the next one is the same type of thing, but kind of backwards. It says, hey, would you convert 2.5 feet into inches? So I'm going to change colors on this, and this is 2.5 feet. I want to convert that into inches. So what's the conversion factor? How am I going to change that? Got one hand up. Now, if your answer on the last one was divide by 12, the end of result of this is we're going to multiply by 12, right? Can somebody tell us what we should do here so that everything works out properly? Lizzie?
You're going to take the fraction that you had before, but flip it.
We are. Because what I want to cancel off is I want to cancel off feet. So I'm going to put feet on the bottom. I'm going to put inches on the top. And I've got 12 inches here. And I've got 1 foot right there. Does everybody agree that this is the same thing over same thing?
Yes.
So this is a funny looking one, right? But that funny looking one is going to allow us to convert from feet, because they cancel, and then 2.5 times 12 is 30 inches. Okay, everybody good there? Okay, now, I always like doing this. Let's see if anybody's got this. Does anybody know how many feet there are in a mile? Feet in a mile. This will be impressive. We're going to go around this way.
What?
Crew,
5,368.
good guess.
5280.
5,280.
5280.
5280. Okay? So up here, this is what I'm going to write down. I'm going to write down 1 mile is 5,280 feet. And we want to change 2 miles. So I'm going to multiply it by a conversion factor. Can somebody tell me what goes on the bottom? Colson?
1 mile.
Very good, 1 mile. What goes on the top? D? 5,280 feet, right? Okay, can you see why I call conversion factors funny looking ones?
Yes.
That does not look like a 1, but it is. Same thing over same thing in a fraction. That is a 1, and look, the miles cancel. And most of you would have known, oh, if it's 5,280, we would just multiply and we get, let's see, 10,560, is that what it is?
Yeah.
Feet, okay? So there's the answer. Everybody good there? Okay, now, remember I said I need your patience here because we're going to go through and we're going to figure out some stuff, a different way to measure angles. So, degrees are not the only, and they're definitely not the best way to measure angles. They're by far what most people are familiar with, okay? But here's how it worked. Degrees, right angle, 90 degrees. They probably chose this centuries ago because 90 has so many factors, okay? So degrees are one way to measure them. Okay, there's another thing called a grad. They use this in some industries and in some countries, and a right angle there has 100 grads in it. So perpendicular is 100 grads. They probably did that because our number system is base 10. Okay, 10s are pretty easy to work with. Yeah.
What's the most common use in general?
What's the most common use or most
commonly used?
measurement?
Yeah.
If you're talking science, then it's radians. What we're going to figure out right now. Okay. So, you will not generally find grads on a calculator, but you will find another type of measurement, and it's called a radian. So write radian right here, and then on your calculator, would you hit the mode button? Don't change anything. I just want you to see that it's on there. Okay? So, there's normal, float, and then radian and degree. Your calculator default is radian. Your calculator default is radian. That should tell you something. If the default is radian, radians are probably better than degrees. But if you need to use degrees, you'd have to come down here, hit enter. But we want to leave it on radian. Everybody good there?
Gotcha.
Okay, so we're going to come back here. You want to take a guess at what the root word of radian is? Luke?
Radius?
Very good. Write the word radius here. So, radians are a way of using the radius, something that every single circle has. Every single circle has a radius, to measure the angle based solely on the fraction of the circle that the angle represents. Now, that is a mouthful and it's a complicated sentence, but that in essence is what a radian is. So, you need to read that last sentence again and let it sink in. Radians are a way of using just the radius, something that every single circle has, to measure angles based solely on the fraction of the circle that it represents. Okay. So we're going to go through and we're going to figure out what a radian is. So this little exploration. So here's the first thing. We're going to label all the quadrantal angles in degrees. So quadrantal is a weird word. So remember, we've got quadrant 1, 2, 3, and 4. We're going to measure all the quadrantal angles. So 0's right here. 90's right here. 180. Hey, wait a second. Didn't we do this yesterday?
Yeah, I believe we did.
270, and then 360 if you get all the way around, correct?
Whoa.
I would write this down.
Okay.
Okay. Let's make an assumption for the purposes of this exploration that the radius of this circle is 1. How many radii does it take to go all the way around the circle?
It'd be a weird number.
What is it? That's how many degrees it is. I want to know how many radiuses it takes. And I asked the warm-up questions for a reason. What is it?
6.28.
6.28. Can you give me how you got that?
Because you have to times it by pi and then 1.
So the formula is 2 times pi times, what did we say the radius was on this one? 1. So this is going to be 2 pi radiuses. So I'm going to write RAD. So we're going to label this distance. So to go all the way around the circle, that's going to be 2 pi to go all the way around. Okay, and I'm going to change colors on this so I can keep these straight. Okay, so this is going to be 2 pi to go all the way around. Okay, if it's 2 pi radiuses to go all the way around, how many radiuses to go halfway around the circle? What is it? 1 what? No, not 1 radius. You're close. Pi, very good. If it's 2 pi to go all the way around, doesn't it make sense that this would be pi to go halfway around? What about a quarter of the way around the circle? Half of a half, right? So half of pi is pi half. Does everybody agree with that?
Yeah.
2 pi to go all the way around if the radius is 1. 2 pi r, radius is 1. 2 pi to go all the way around. Pi to go halfway around, and pi halves to go a fourth of the way around. Everybody good there? Okay. So halfway around was pi. A fourth of the way around was pi halves. Now I want you to draw a radian, and I'm going to tell you what a radian is in degrees. It's not exactly 57 degrees, but it's pretty close to 57 degrees. So what I want you to do is I want you to draw a central angle that's about like that. I want you to label it as 57 degrees. And then this out here is 1 radian. In other words, it's 1 radius, right? Hang on 1 second. So that arc length is 1 radian or 1 radius. That central angle is 1 radian, which is 57 degrees roughly. Okay, Luke.
So I plugged 360 divided by 57 into my calculator, and it's 6.31, which I think means that the radians don't go into a circle evenly.
That's because I rounded the degrees. It will go in there. About 6.28 is what the answer should be. We're within a couple hundredths of the answer there. Okay, so hang on just a second. Okay, what if the radius wasn't 1? What if the circle got bigger or smaller? Okay, so if the circle was bigger or smaller than a radius of 1, the size of the circle would change, but I want you to notice something that we talked about yesterday. The central angle would not. So I'm going to take this and I'm going to draw something else, or I'm going to change colors, and I'm going to draw a circle about like this. Is the central angle the same? It is. Is the radius smaller? Yes. But if I take that radius and I go along here a little bit, that's still going to be 1 radian. Okay? So if I take this long length right here and stretch it along the outside, it's going to be 1 radian out there. If I take this shorter one in here and stretch it along the outside, it's still going to come to the same place on the circle. Okay? We okay with the idea? Okay. So here's what we want. It's still going to be 360 degrees in a full circle. It's still going to be 2 pi radians to go all the way around. It's still going to be pi radians to go halfway around. And 1 radian is still going to be 57 degrees. Yeah?
Is 57 degrees just a fancy number we use in numbers?
No. It's just in a ballpark. I'll show you how we got that in just a second. Hannah, can you pull the door shut? So notice up on the diagram we've got a couple things. So I'm going to highlight these. Degree measure for half a circle is 180. Radian measure for half a circle is pi. And degree measure for a full circle is 360, and radian measure is 2 pi. So if we take the fact that we've got the two of those things marked, pi is the same as 180 degrees. 2 pi is the same as 360. So, using what we did in the warm-up with conversion factors, can anybody see what we can do to make a conversion factor to change from degrees to radians? So let's say that I had this. So would you write this down, please? 90 degrees. And I wanted to change that to radians. What's a conversion factor again? A funny looking one. What unit would need to go on the bottom if I'm going to cancel off the degrees? Degrees. Okay? Now, regardless of which one you take, these two things equal each other, right? So if I did pi over 180 degrees, or I did 2 pi over 360 degrees, this one you can't do anything with. What happens with the 2 pi over 360? Doesn't it just turn into this? If I cancel here, I get 180, right? So what I'm going to multiply by is 180 degrees and put a pi up here, correct? Okay. Everybody agree the degrees cancel?
Yeah.
90 goes into 180 twice.
Yeah.
So if I change 90 degrees to radians, I get a pi on the top and I get a 2 on the bottom. So I get a pi on the top and a 2 on the bottom. Isn't that what we kind of reasoned our way to just a second ago? Everybody good? Okay. Down at the bottom of the page, it's got a couple problems where it just says convert 90 degrees to radians. Done. This is pi halves. 45 degrees to radians. 45 degrees. If I want to cancel off the degrees and change them to radians, I need to multiply by 180 degrees on the bottom so that those will cancel. And I'm going to have a pi on the top. Those will cancel. Pi on the top. What do you get on the bottom? 4. Okay. So pi fourths. Now, before I forget this, there's some people that say you have to put the word radian on the side of this. Okay, you do not have to put radian on there. If you don't put a measurement on there, everybody assumes that your measurement is in radians. Let me say that again. Everybody assumes a measurement is in radians if you don't put a unit on there. Okay, because it's just a plain old real number. Okay, now 30 degrees to radians. Would you go ahead and change that? Somebody tell me what it is. Yeah. Pi over 6. Okay, so we got those. Now, before we flip the page over, I want to come back up here and take a look at one more quick thing. Okay, 45 degrees is a common angle, and you all know that, right? 45 degrees, do you agree, would be about right here? A little bit less than 1 radian. You agree with that? Okay, would you type into your calculator pi divided by 4? 0.79. Okay, so is that a little bit less than 1 radian? 0.79 radians? Okay. Would you type in pi 6 into your calculator? What'd you get? 0.52, so about half. Would everybody agree that if I marked a 30-degree angle on here, 30 degrees is about half of 57? And didn't we just figure out that this was, what, 0.52 radians? So can you see how these kind of match up? Okay. You don't have to remember 57 degrees. Okay. What you do need to remember is the common angles, and you've got to know these conversion factors. So flip the page over. So we're going to summarize radians so far. So here's the deal. Radian means, what does it mean? Where'd they get the word? Radius. Radian means radius. A radian is a fraction of the circumference of a circle. And it's based off the radius. And every circle has one. Radian is a real number. And it doesn't have a unit. We don't have to worry about units anymore. If you're measuring things in radian, it's just a number. No units on it at all. Okay? And we can use 180 over pi or pi over 180 in order to convert between radians and degrees. And this little thing at the bottom right here, I'm going to put a star by it. Because remember, the way you figure out which one you're going to use is you want to say, well, I want to cancel this off. So if you want to cancel something off, you put it on the bottom because it would have already been on the top of the original one. Okay? So put a star by this. This is the goal of the lesson because we want to be able to understand and use radians. Radians are just another way to measure angles. So we need to be good at using both radians and degrees. So if you need to, this is what I would kind of lock in your head. This picture that we kind of constructed on the front side, this is 0. 0 radians, 0 degrees. Half a circle is 180 degrees, which is also pi radians. There's your conversion factor right there. You could do the 2 pi and 360 if you wanted to, but there's really no need for that. So notice this doesn't have any units on it. We want to change pi thirds into degrees. Whoops. So the degrees are going to be on the top. The radians are going to be on the bottom. Do you notice what happens? Yeah. The pi's cancel. The only thing left, the only thing left is 180 over 3, which is 60 degrees. So pi thirds is exactly the same as 60 degrees. We already know what pi halves is, but let's check and make sure that this actually works. So we want 180 degrees here. We want to cancel off the radians, so the radians go on the bottom, the pi radians go on the bottom. Those cancel. 180 divided by 2? 90. What are the units? Degrees. Those are left. Okay? So we've converted that one both ways. Would you change pi 12ths into radians? Sorry, pi 12ths into degrees. What'd you get? Crew?
15 degrees.
15 degrees. Thanks for throwing the units on there. Okay. Any questions there? Okay. I'm going to call on Jack. Jack, what are we going to multiply here? We want to convert from degrees into radians.
By 180 degrees.
Where? Top or bottom?
Bottom.
Bottom. 180 degrees on the bottom, pi radians on the top. Yes. Degrees are going to cancel. Now we have something with no units. We've got a measurement with no units anymore. So 135 divided by 180, I'd kind of get used to this. Do it on your calculator if you need to. What fraction is it?
3/4.
0.75 or 3/4. So that's, we say 3 pi fourths. Okay. Next one. Same conversion factor. We're going to put the 180 degrees on the bottom. We're going to put the pi right here. The degrees are going to cancel, so we've got a measurement that does not have any units, which is nice. We're going to have pi on the top. You don't need a calculator for this, watch. I'm going to cover up the zeros. I've got 27 over 18. What goes into 27 and 18 evenly?
21.
Oh, 21. 21 and 18 evenly. 3, right? 3 goes in here 7 times. 3 goes in here 6 times. 7 pi 6 is the way we say that. Now, you should know the answer to this, but let's just double check and confirm using the conversion factor that this actually works. That doesn't have units on it, so it's a radian. So I'm going to change from radians to degrees. So pi is going to go on the bottom, 180 on the top. Those are going to cancel. Didn't we say pi is exactly the same as 180 degrees? Okay, any questions there? Okay, radians are just another way to measure angles, and they're convenient because they don't have any units. No converting or anything from one system to the next. So come down here and take a look at this. These are the formulas that we did yesterday. That's the formula that you have to use if it's in degrees. You have to figure out the fraction of the circle out front, and then we've got the formula for the circumference. Fraction of the circle out front, and then we've got the formula for the area. Does anybody notice anything about this right here?
We did that.
Zach?
It has degrees and radians.
It does. It has 360 degrees on the bottom, and it has 2 pi on the top. Aren't those the same thing? So couldn't I just cancel those off?
Oh.
So if it's measured in radians, the only reason we had that theta over 360 in the front is because it was measured in degrees. If you measure in radians and they don't have any units, those will cancel and we get theta times r. Now tell me that's not an easier formula. That's way easier, isn't it? Okay? Now take a look at this. This takes a little bit of thought. Do you see what we can do with this one? There's 2 tricky things we could do. One, we could do pi over, and we could change this to 2 times 180. And then I can cancel those. Or I could be super tricky and do this. Times by 2 on the top and times by 2 on the bottom. 2 pi will cancel with 360. So here's the formula. You know it? You see what it is? Theta divided by 2 times r squared. So I'm going to make those the same size. That's still an easier formula. Okay? So off to the side here, this should kind of make sense because the only reason we put the theta over 360 was so that we could find the fraction of the circle represented by the sector. And a radian does that automatically. Okay? So you're going to need the measurements that we were just converting, so I need to make this just a tad smaller. Okay? So on this it says find the arc length and the area, radius of 5 and a theta, an angle of 135 degrees. But let's change that to radians. You got the answer up here. 135 degrees is 3 pi fourths. That's how we say this. So I'm going to cross this off and I'm going to say 3 pi fourths. 210 degrees. We're going to do it in radians, so that's going to be 7 pi sixths. We good? Okay, let me make this full size now. Come back here, and this is all we have to do. Length is going to be theta, 3 pi fourths, times the radius 5 centimeters. I'm going to change colors. The area is 3 pi fourths divided by 2 times the radius squared. Okay. Kind of a story problem, right? Grab your calculator, type this into your calculator. Do 3 times pi times 5 divided by 4. Psi.
Could we just do 135
No, I want you to use the formula like it is.
You can.
I'm not sure I understand the question, and I'd want to make sure I'm thinking through it. So let's
You
see.
can, I just did it.
11.78?
Yeah.
Okay. Whoops, let me change colors here. 11.78, and that would be centimeters. And let's see, this one is, okay, take a look at this one. Okay, this is called a complex fraction, so I'm going to make this a little bit bigger so everybody knows how to use these. We're going to take this, and I would flip it over and I would multiply, so this would be 1 over 2. So the easiest way to put this in would be 3 pi over 8, kind of like half of 3/4, times 5 squared. Okay? Throw that in your calculator, and would somebody tell me what you get?
9.45.
9.45?
29.45.
Say that again?
29.45.
29.45? Is that right? 29.45, and that would be centimeters squared, right?
Yeah.
Okay. All right. This one right here would just be 7 pi 6 times 10. Answer's going to be in meters. And then this one's going to be 7 pi 6 divided by 2. And then we're just going to do 10 squared, and that would be in meters squared. Okay. Somebody got the length? Luke.
36.65 meters,
Okay.
approximately.
Is that right? We good there? Okay. And then the other one, the area? Si.
183.26.
183.26?
Yeah.
Okay, square meters. Okay. If you compare those with example 3, we actually did these yesterday. We did, but we used the different formula for that. Okay?
Mr. Laws, don't forget to take scores.
Ooh, thanks. I mean, we may or may not have time.
You have about like
Is it
15
match?
seconds left in the
Okay. Wilson looked up his answers from yesterday and they match. So these formulas work.
I think we should get multiple history.
You think so, huh? Hang on a
What
second.
Simon's saying was
Okay,
like-
listen up. Hold on. Okay. You don't need to memorize both of those formulas. What you need to be able to do is convert from radians to degrees or degrees to radians. So you need to know one of them. I would prefer you know the ones in radians. Okay? They're better in the long run, they're more useful, and I guarantee you're going to see them again. Here is what we want to do. This. You need to be really good at understanding radians and using them to represent common angles. So, hey, we're almost done. Here's the assignment. You'll notice that most of this, these are just questions about how we convert and the relationship between radians and degrees. This is converting from radians to degrees or degrees to radians. Couple arc length formulas, couple area of sector formulas, and then this right here is really the goal. You can go all the way around the circle and all of those common angles between 0 and 360, hold on, you know them in radians and degrees. So of everything on there, this is by far the most important. You need to do the whole assignment, okay?
Thank you,
To
Mr.
do everything,
Laws.
all right. Okay, see ya. We'll take scores tomorrow. You'll live.